This video is brought to you by mywayteaching.com.
So, in this part, let us consider a very simple problem. To simulate car accidents, auto manufacturers study the collisions of moving cars with mounted springs of different spring constants. Consider a typical simulation with a car of mass 1000 kg moving with a speed of 18 km per hour on a smooth road and colliding with a horizontally mounted spring of spring constant 6.25 into 10 raised to 3 Newton per meter. Okay, so what is the maximum compression of the spring? So this is the given question here. They have given some data. So based on that data, we should find out what is the maximum compression of the spring. See, at the maximum compression, the kinetic energy of the car is converted into completely or entirely into the potential energy of the spring. So, the kinetic energy of the car is given by half mv square, isn't it? And here they have given the value of mass as 1000 kg and velocity they have given in terms of kilometer per hour. When you convert it into in terms of meter per second, you will get it as 5. So the value of k is 1.25 into 10 raised to 4 joules. So again we have converted 18 kilometer per hour to 5 meter per second. So it is easy if you remember, for 36 kilometer per hour it is 10 meter per second. See, at maximum compression, that is xm, the potential energy V of the spring is equal to the kinetic energy K of the moving car from the principle of conservation of mechanical energy. Okay, the potential energy is equal to the kinetic energy. So that is given by V is equal to half km square. So that is also equal to 1.25 into 10 raised to 4. So by using these we obtain xm as 2 meters. Okay. So let us consider some of the remarks on conservative force now. So the first remark is information on time is absent, which means we can calculate the compression but not the time over which the compression occurs. Okay. A solution of Newton's second law for this system is required for temporal information. Okay. So this is the first remark. Coming to the second remark, not all forces are conservative. Friction, for example, is a non conservative force. The principle of conservation of energy will have to be modified in this case. Okay, since all are not conservative force, we should modify the principle of conservation of energy. So, that is the second point. Okay. So, moving to the third point, the zero of the potential energy is arbitrary. It is set according to convenience. Means, for the spring force, we took V of x is equal to 0 at x is equal to 0. That is, the unstretched spring had zero potential energy. For the constant gravitational force mg, we took V is equal to 0 on the Earth's surface, isn't it? So the zero is best defined at an infinite distance from the gravitational source. However, once this zero of the potential energy is fixed in a given discussion, it must be consistently adhered to thought throughout the discussion, isn't it? So you cannot change horses in midstream. So this is the so no, all these three were the few the what we can say views or the important remarks on conservative forces. So moving to the next example, that is example number 9. Taking the coefficient of friction, that is mu is equal to 0.5, calculate the maximum compression of the spring. So that is the question. See, in presence of friction, both spring force and frictional force act as to oppose the compression of the spring. So you can see that in this figure. See here, both the spring force, that is Kx, as well as the frictional force, you can see here, both they oppose each other. Okay, the frictional force act so as to oppose the compression of the spring. So we invoke work energy theorem rather than conservation of mechanical energy. Okay, so the change in kinetic energy is given by what? It is delta K, isn't it? The change in kinetic energy. So we can write it as Kf minus Ki, isn't it? Yes. So we know the change in kinetic energy is zero in the final state, and in the initial state it is half mv square. So the work done by the net force, we can consider the work done by the net force, that is given by W is equal to half xm square minus mu m gxm, where mu mg is the frictional force, xm is the displacement. So equating this w with the delta k, we'll get half mv square is equal to half kxm square plus mu mgxm. Okay, so now let us calculate mu m and g, where mu is given it as zero point 0.5 and mass is 10 raised to 3 and g is 10. So we'll get it as 5 into 10 raised to 3 Newton. So by considering g is equal to 10 meter per second square. So after rearranging the above equation, we obtain a quadratic equation with the unknown term xm. So we can write that quadratic equation as k xm square plus 2 mu m gxm minus mv square is equal to 0. So xm is equal to minus mu mg plus mu square m square g square plus mkv square 1 by 2. divided by k. So where we take the positive square root since xm is positive. So putting in numerical values we obtain 1.35, isn't it? So if two forces on the body consist of the conservative force Fc and the non-conservative force Fnc, the conservation of mechanical energy formula will have to be modified. In that particular case, we will modify the law of conservation of mechanical energy, that is given by, okay, that is given by putting in numerical values we obtain the value of xm is equal to 1.35 meter. Okay, so if the two forces on the body consist of a conservative force Fc and a non-conservative force Fnc, the conservation of mechanical energy formula will have to be modified by the you know work energy theorem. So that is given by, so Fc plus Fnc delta x is equal to delta k. Fc into delta k is given by minus delta v. So delta of, so that is given by Fnc, that is non-conservative force into delta x. Okay, so we can write delta E is equal to Fnc into delta x, isn't it? Where E is the total mechanical energy over the path. So this assumes the form Ef minus Et, or we can say Ef minus Ei is equal to the work done by the non-conservative force. Okay, so where Wnc is nothing but work done by a non-conservative force, okay, over the path. See here, WNC depends on the particular path, that is I to F. It's not like the non, conservative code force. Since this is a non-conservative force over the path, it depends on that particular path, that is from I to F. Okay. that is the non-conservative force.